Hi everyone! Today I will present our work on distinctiveness maximization in datasets assemblage. We start from a common data preparation pipeline with 3 stages: data cleaning, datasets discovery, and tuples discovery. However, we identify a gap in existing datasets discovery work. Most existing methods evaluate each candidate dataset individually, typically based on its similarity to the user input. But when datasets are assembled together, substantial redundancy may arise across them. Moreover, these methods often implicitly assume that users can afford to use all discovered datasets. In practice, users usually face a limited budget and therefore care about the return on investment. So to fill this gap, we study advanced datasets assemblage, where we evaluate the usefulness of the dataset collection as a whole and assemble a useful set of datasets under a budget. Our problem has 2 key ideas. First, we use a query set to capture the user's fine-grained information needs. Second, we introduce distinctiveness to evaluate a set of datasets. Intuitively, distinctiveness measures how many distinct tuples a dataset set can provide for the query set. The goal is to select a subset of candidate datasets that maximizes total distinctiveness under a budget. As this example shows, different dataset combinations may contribute different amounts of new information because of overlap. Here, D5 and D10 achieve the highest distinctiveness because together they cover more distinct tuples. However, this problem is challenging for 2 reasons. First, finding the optimal dataset combination under a budget is NP hard. Second, even with a greedy strategy, exact distinctiveness computation remains expensive because it requires checking tuple overlaps repeatedly. In our experiments, this can take around 1 hour for only 20 datasets and 10 queries. To address this, we propose ML greedy, which uses ML-based distinctiveness estimation instead of exact computation. To estimate distinctiveness effectively, the key challenge is how to effectively and efficiently identify the 2 types of overlaps in the results of a query set among different datasets. To this end, our ML-based distinctiveness estimation method consists of 5 components. The first part, including components 1 to 4, estimates the distinctiveness of a dataset by identifying overlaps in the results of a query set within a dataset. The second part, component 5, merges data summaries to identify overlaps in the results of a query set across multiple datasets, enabling us to estimate the distinctiveness of a set of datasets. Specifically, to estimate the distinctiveness of a dataset, we first generate a data summary for the dataset in component 1 offline, and then capture the connections between the queries and this data summary in component 2 online. Next, in component 3, we represent the information of a query set to capture the connections among the queries. We then combine these learned representations to estimate distinctiveness of a dataset. After estimating the distinctiveness of a dataset, we next consider how to estimate the distinctiveness of a set of datasets. To this end, in the second part, we merge the data summary of the current set with that of a candidate dataset. This allows us to estimate the distinctiveness of a set of datasets efficiently without scanning all tuples again. Together, these 2 parts form the key idea behind our ML-based distinctiveness estimation. Our experiments show 3 main results. First, for distinctiveness estimation accuracy, our method is substantially better than the state-of-the-art method. Second, for datasets assemblage effectiveness, ML-greedy is highly competitive with exact greedy, with a distinctiveness ratio close to 1, while also outperforming the other baselines. Third, for efficiency, our ML-based distinctiveness estimation method is much faster than exact computation. Our method to merge data summaries is also much faster than competitors. And overall, ML-greedy is generally around 2 orders of magnitude faster than the alternatives. Overall, these results show that our approach is both effective and efficient for distinctiveness maximization in datasets assemblage. That's all. Thank you.